Big whales have little whales, which feed on their velocity, and little whales have lesser whales, and so on to viscosity. This is actually something very kind of dear to my heart. I did my PhD in the Center for Turbulence Research, and I think very much most people who are familiar with fluid mechanics and turbulence knows this little poem, right? And a lot of us also knows this poem is written by Louis Fry Richardson. But I find most people I talked to didn't know where is the original citation of this poem from. It turns out to be in a book called Weather Prediction by Numerical Process. And what's remarkable is that the year of the book's publication is 1922. Okay. Weather Prediction by Numerical Process, 1922. That's almost 30 years before the first digital computer actually came online. So today, I'm going to be doing something not like a standard talk. So there will be no equations, not even numbers, I think, well, other than 1922 is probably one of the in my talk. But I'm going to give you three stories in the sense of big worlds and little worlds and smaller worlds. So the biggest story is a story of Louis Fry Richardson. And within that, I want to give a story of Flexcompute, our company. And lastly, closest to viscosity is my personal story and the instrument I'm learning to play, the flute. Okay, so why did I start with Richardson? Because Richardson, as you can see, he's a dreamer. So he's somebody with big visions and big dreams. And 30 years before there is digital computer, he envisioned the whole process of solving numerical differential equations in a process that's actually faster than how the weather actually evolves, right? Real-time engineering. And at a time where it is basically impossible. And but by the way, at that time, he is an Englishman, and by that time, especially in England, weather is synonymous to unpredictability, right? So, and 30 years before computers, this just is unimaginable. I want to tell this because at Flexcompute, the reason we started Flexcompute is also because we have a dream. We have a dream that's equally, or maybe you can say even more ambitious than Richardson. And this is the second story I'm telling here. So, okay, so why did we found the Flexcompute, which is almost 8 years ago? So this is because I did my PhD at Stanford in computational mathematical engineering, and then I went to teach at MIT. And all these years, I found all the smart students, they all went to software. Very few people who stayed, and even those who majored in aerospace engineering, very few actually stayed to do aerospace engineering. They all went to Google, finance, whatever that does software. This is really because hardware innovation somehow is much, much slower than software innovation. Just to think about when I was young, like all these science fiction books is predicting by today, we are taking vacations on Moon and Mars and things like that. But instead, this is what we get, like internet, social media, and AI. Okay, so why is this? Why is software so much faster than hardware innovation? Well, we all have the answers, right? I mean, there is risk, right? People die when you fly hardware that's not that carefully designed and made, right? The cost is huge, and unless you actually do some hardware, it's very hard to just even appreciate just how much time it takes to carefully test anything. And the dream of Flexcompute here is we want to make hardware innovation as easy as software innovation. We want to make people, okay, you can have a small team or even an individual. If you have a big idea, you should be able to use simulations to test out this idea without risk, with very little cost and with very little time. I don't know when, but maybe 30 years in the future. right? So this is why we started the whole thing. And well, how are we doing this? So let me first get back to Richardson, like how he's envisioning the numerical weather prediction to happen 30 years before there is computers. Well, so the dream of Richardson is the following. So I'm just reciting what he had in his book. After so much reasoning, may one play with a fantasy? Imagine a large hall like a theater, except that the circles and the galleys go right around through the space usually occupied by the stage. So no stage. Everything just goes around circles. And the walls of the chamber are painted to form a map of the globe. The ceiling represents the North Pole, and England is in the galley, and the tropics in the upper circles, Australia in the dress circles, and Antarctic in the pit. Okay, a myriad of computers. Well, what he means by computers? People whose job is to compute are at work upon the weather of the part of the map where each sits. But each computer attends only to one equation on one part of the equation, basically a grid point. That's what we call today. The work of each region is coordinated by an official of a higher rank. Okay, so maybe a rank in terms of our MPI process, right? Numerous little night signs display the instantaneous values so that the neighboring computers can read them, and each number is thus displayed in 3 adjacent zones so that to maintain communication to the north and south of the map. So it's basically transferring information between adjacent ranks. So this is basically CFD, right? Except for it is many, many years ago. And I just asked the AI to generate a picture according to this kind of a description. And this is what I got. That's how he's imagining CFD to work for numerical weather prediction. Now, getting back to Flexcompute, what are we doing? Well, we want to start somewhere, right? So basically the idea is to, we want to just make things faster, like 100 times faster and at a lower cost. That's basically what we are trying to do. And so this is the product, like Flow 360. I didn't even list it anywhere. So basically Flow 360 is the product, and it's integrated meshing, simulation, post-processing, and you can drive it by like a Python API or with a web browser. It's the same thing. And there is a list of features. I think this audience may not be the right one to talk about all the features, but let me actually just get to one other next stage of the story. That's what did the people and Flexcompute did specifically. So Richardson is not just a dreamer. He didn't just dream this thing. He actually tried it out. So what exactly did he try out? He actually did a calculation by himself and maybe with a few assistants he at that time. So he spent 6 entire weeks with his assistants doing calculations and produced a 6-hour forecast of a region I think is half of the size of Germany. Okay, and so basically, well, it's not really real time, right? And it doesn't even cover the entire globe. So it's actually orders of magnitude slower. But this is actually kind of a proof of what can be done, right? Just imagine if this thing happens at a more streamlined way and with more people. So this is basically numerical weather prediction. He was trying to show that it is possible. Okay, so now this leads to my third story. That's my own story. So I'm at Flexcompute. We're trying to do a demo like similar to this. And this is the instrument. I started learning about a year ago. I think I can pass it around. And why did I start on this instrument? So a big influence is by Professor Jameson. Okay, so similar to Richardson, Jameson said something that influenced me a lot. any mechanical engineers can do structure and control. Only aerospace engineers can do aerodynamics. And Professor Jameson said that in one of the lectures I attended at Stanford. So this is the instrument that I started playing like a year ago. And the flute is one of the instruments that produces sound not by any other means other than vibration of the air. So it's a pure aerodynamic instrument. I mean, if you look at it, there is nothing that is supposed to move or vibrate or anything like that. It's the air that is doing all the vibration. And just to make sure, I actually 3D printed one of these, just to make sure, like, if I do it with any material, it works exactly the same. All right. So this is I want to show you one of the simulations, what we can do with the Flexcompute's Flow 360 software of simulating the sound of a flute. Okay, so here's in light of Professor Jameson's typical way of doing things, I'm going to, I need to mirror my display, I think. To duplicate my display. Yeah. And so new project, I'm going to start a new project. I'm going to upload a step file. So people who work in the more practical side of CFD knows, like, step file is a typical geometry format we use to exchange between like a CAD and a simulation. So Jameson demo, and I know my step file has a unit of millimeters. Okay, submit. Okay, so the geometry is being uploaded. Hopefully, okay, yeah. Sorry. Oh, I didn't mirror it. Oh, it went back. Oh, I think I have to say, yeah. Okay. So when it is uploading, let me just tell you a little bit of how a flute works. So when you're blowing against the lip of the flute, there is a sharp edge. Okay, so the stream you're blowing is split almost in half. Half of it goes out of the flute, half of it goes into the flute. Okay, so now imagine if the region in the flute near the mouth has a lower pressure than outside atmosphere. Then the lower pressure is going to pull the stream more into the flute, right? So you have a larger mass influx into the flute than on average. And the mass flux increase is going to cause the density to increase near the mouth, and density increase is going to cause the pressure increase, and the pressure is going to push the flow downstream to move faster. So there is going to be a pressure wave moving towards the end of the flute. And when the flute reaches the end, it's open. So the pressure wave actually reflects back in a negative way. So it comes back and it impinges on the embouchure. Basically, when the air is again pulled back again. So basically, the air vibrates out and in. When it vibrates out, the mass flux is lower. It creates a negative pressure. It amplifies the negative pressure, and when the negative pressure is there, it comes in, right, and creates a higher pressure. So it basically oscillates that way. And just feel free to blow it if you have the flute at some time. Not edit project. So now I go to the project. It should just load up the geometry, and that's basically the flute. I think Fei-Ling actually did all of the work starting. I think he put the fluting Black Friday. So yeah, thank you for working just overtime for getting the simulation in and done. Okay, so basically we simplified the outside of the flute, but inside, especially the region near the lip, is pretty well worked on. And the only thing you need to do a simulation. So here I'm just going to do a example simulation, not exactly producing sound, but I'm going to make a 1 millimeter. So this is all the input you need, right? You want to input what is the max edge length of the surface mesh? What is the boundary layer thickness? I'm just going to put a 0.01 millimeter as the thickness. And the operating condition, I'm just going to assume the Flute is an airplane. I'm going to put a 100 meters per second velocity. And I think the Flute is oriented in the Z direction. So I just want the air to go through. So what is the angle of attack I should put in? 90, yeah, thank you. Okay. Okay, 90-degree angle of attack. Okay, so one of the things is we are having a beta measure. Like this is going to be the extremely fast next generation measure we have over here. You click run and it starts the surface meshing, volume meshing, and the case. Okay, so when this is running, let me just show you a little bit of the existing simulation we have done to produce the sound. So this is, I think this is the one Failing actually ran to produce the sound, and show you what's the difference between this simulation and that. So other than setting up the conditions, the first thing you're going to notice is the time stepping. It's going to be an unsteady simulation. Yeah, where's the time stepping? Yeah. Okay. So so it's actually, there is a series of simulations. So starting maybe this many time steps, but like with a consistent time step size. Okay, so each time step is, if you count the number of zeros, it's 12 microseconds. Okay, so 12 microseconds time step. And every time step, physical time step, we are basically following Jameson's method of doing dual time stepping, right? So every physical time step has 30 pseudo steps inside. So basically converging that unsteady time step. And is there any, there's a ramp CFL. Do we have control of number of linear iterations inside? Okay, anyway, so basically every pseudo step now has, I think, 25. Did you change the default? Is 25 linear iterations? Oh, 30. Okay, so every pseudo step has 30 linear iterations. So basically every one of these 12 microsecond time step has 30 times 30, so 900 linear iterations inside it. So that's kind of for you to appreciate. I think this is the right audience for you to appreciate, like, what is the amount of computation done over here, right? In every time step. So yesterday there was a presentation like simulating a combustor where there are pressure waves going on. I mean, it's basically a wind ensemble, right, going on. And they simulated the 10 milliseconds, and 10 milliseconds is actually an awful long time, right? Considering how small of time step size you have to run and how many things you have to do within each unsteady time step. So getting back to our original simulation, so the surface mesh has been done. So that's kind of the that's if you I don't know, can you see that clearly here? Yeah, I don't have a mouse here, so zooming in just on the trackpad is a little bit difficult. So that's kind of the mesh resolution we have, and with all the holes and stuff. And if you look at the volume measure, so we are basically doing it in a very traditional way. So we generate the boundary layer mesh and then the far field mesh. The boundary layer mesh basically is the viscous layers, right, to resolve the boundary layer. And then there is a glue measure that glues the boundary layer mesh and the far field mesh. And maybe I just want you to see a little bit on the kind of a mesh we typically generate for actual applications. So this is for a car with ended up with 40 million nodes, and right now this thing took like 10 minutes, but like we are going to so there is a lot of improvements on the way. That is still beta version. It'll be basically lightning fast very soon. Okay, so the volume measure in this case has finished, and it's waiting for resources to start the job, to start the CFD simulation. So let's see if it gets picked up soon or not. Okay, so it's picked up and the case starts running. What else do I want to show? Okay, so back onto the simulation we actually did for the Flute, right? One of the things I may want you to look at is the number of simulations we have done. So basically, we have a simulation that's actually forked. Forked means use the final solution of the previous simulation for the next simulation, and then you can focus. Like, so the reason it's a tree is because the geometry can have multiple surface meshes. A surface mesh can have multiple volume meshes. A volume mesh can have multiple simulations, and a simulation can fork arbitrarily many like sub simulations. So this is the kind of stuff we have to do. It's stuck at. Okay, so started processing the mesh. Why is it the sim visualization not showing? So what I want to show you is over here we put a bunch of monitor points. We put a bunch of monitor points, and that's basically to record the pressure fluctuation, right, on the flute, so that we can actually look at and even hear what the flute is actually making through this CFD simulation. That's why the talk of my title is hi-fi, right? High fidelity. I mean, if you look at the Wikipedia, high fidelity doesn't mean high fidelity turbulence modeling. It means high fidelity production of sound. And now we can do it actually with the CFD. All right. And okay. So the solver on the steady state flute case has started, and so we will basically be watching the convergence, right? So how I think for this case I shouldn't have set a turbulence model because the real sample is probably very small, but like I think the default is a Splato-Mars turbulence model. So you'll be seeing like continuity equations, 3 momentum equations, energy equation, and the new head equation. So that's how things are going. So it doesn't update all the time, but like basically after once in a while, it'll update how the residual goes, and we can see the advancement of the simulation. So the conservation equations usually converges first, and then the turbulence model equation drops down after the conservation equations converged to somewhat. And I think the default is usually just similar to 2000 iterations. Yeah, so we can just watch this, and it'll be done pretty soon. Yeah, now the turbulence model is also going down. If you really want to converge this simulation, probably you need more than 2,000 time steps. But yeah, it should be done in a minute. Okay. Should I just wait? Yeah, now it's done, right? 2,000 steps, and it's if you want more, you can just fork the simulation to run for longer. Do I get a visualization here? Okay, so anyway, so I can show you how the result looks like. So here's VS Code, and I have a code that basically goes to the internet. I mean, you can just do Python using import flow360, right? Or from flow360 import all, and you can have basically we have case IDs. So this is the last case ID of every group. The code basically looks for all the parents of this ID, right? And just loads all the data and tries to plot the pressure distribution on one of the. Can I have Flute? Yeah. So basically the point is roughly over here. The point I'm recording the pressure. Actually, it records everything, including the pressure. So it's roughly sitting over here. So that's usually, for example, if I play it like this, the microphone is here. That's basically what it is recording. Okay. And one of the things we didn't have time to do is because we set it up like almost exactly a week ago, like in actually Black Friday, that's exactly a week ago, is that if you try this, it's not easy to produce a sound. So what we didn't do is, I actually want to show you how we set up the simulation. So let's see if I can get a visualization running. Change to a different case. Oh, okay. I actually just okay. Yeah. So the way we get it working, which I didn't set up in that steady state simulation, is that we put an actuator disk over here. So an actuator disk is usually used to simulate propellers for airplanes, right? And here I just used to simulate the mouth, kind of the blowing of the mouth. But the thing is, propellers are circular, but the jet from the mouth is not. So I put two porous media zones up and down to block the flow. I put kind of the Darcy coefficients to something that's ridiculously high. Basically, it's solid. So basically, there is a roughly flat jet kind of coming out of in between the porous media from the actuator disk. Okay, so that's how this is simulated. And if you look at all the monitor points, yeah, the outside one is, yeah, so these black dots are all the monitor points. Outside one is, which direction is outside one? Oh yeah, that's that point. That point is outside one. Yeah. So basically, we'll be looking at. We are actually looking at. If you look at the thing I plotted, right? I'm looking at the pressure at that location in pascals. So for those of you not that familiar with acoustics, so 1 Pascal fluctuation is very loud. It's like a 94 decibels. So every time you go lower a factor of 10 in the raw pressure, the decibels goes lower by a factor of 10. Not by a factor of 10, goes lower by 10. So this thing, I mean, if you look at the sound over here, maybe it's 70 something decibels, right? So it's kind of so here it's making sound, making good quality sound. Here it's not. Here it's like almost not producing much noise. And if you zoom into here, let's maybe look at it slowly. So if you look at, this is kind of the start of the sound generation, and I think for the C note in the beginning, like C note is the what we call the root note. That's like the C note, and in the beginning, there are 2 main harmonics going on, right? One is the lower frequency, and it's superimposed a higher frequency. But later on, as the nonlinearity comes in, kind of the higher frequency drowns out the lower frequency. That's also not what I intended. I intended to be basically like in flute, you have exactly the same fingering, and you use how you blow it to control how you produce the higher note or lower note. So we ended up producing the higher note. And here is the fingering changed. So I used a bunch of porous media to block the holes, right? And I changed this. I changed the fingering. So that's kind of the transition of this sound going on. And I actually recorded a bunch of transitions and compared it against this. It looks qualitative similar, but this sudden increase is not there. And I think at this point, my conclusion is that if I run plot wave with my recorded sound, the sample.wave, I recorded the 3. So basically, in the transition region, you do see kind of the sound that suddenly ramps up with the changing frequency. But I think my finger cannot get away like instantaneously, right? If you look at this amplification, instead of instantaneously, I have about maybe 0.03 seconds time of going up. Okay, so I think, am I running out of time? Yeah. Okay.
Maybe yeah. Maybe.
So let me
wrap up in 2 minutes.
Let me wrap up.
Yeah. Wrap up.
Okay. So anyway, so the conclusion is that we're able to simulate, I think, in 2 days, right? Is it we ran it for 2 days? Less than that. Okay. Well, but we did it in parallel. So because of the sound that we split the sound into 4 different sections and simulated we ran 4 simulations, I think, for less than 2 days, and we produced 11 seconds of sound. Okay, so instead of 10 milliseconds, we're producing, I mean, if you look at the whole thing, like it's 11 seconds of sound. And if I play the sound in my favorite media player, which is Visual Studio, So that's what we are able to produce. And now let's go. So maybe just to look at some animation. So this is a really like how the sound is produced. That's kind of just a outline being pushed and pulled by the pressure wave, and on the left is the pressure wave kind of going back and forth. And this is one of the transitions where initially I have the bottom holes open, so the pressure wave is going only on the upper side, and then suddenly close the holes, and things just gets different. Okay, so let me conclude. Well, I just there are other things that can produce sound, and so okay, so go back to Richardson's example. 30 years after numerical weather prediction book, computers are invented, right? And finally, people get to actually real-time engineering. Like the process for which we can simulate weather now is faster than how the weather proceeds itself. And that starts to produce useful things, right? I mean, you can actually forecast the stuff rather than just keeping up. And for Flexcompute, this is really the dream of being able to make people, enable people to, for example, if they want to make a new flute, right, to do the simulations rather than having to drill wood or something like that. And not just for musical instruments, but like for really important things like aerospace applications. All right. And finally, I just want to play this sound again. And may the force be with you, Anthony.